Alright, FST, you can hold it together. I just realized that I'm going to make this 10.6 video, then there's a 10.7 video, and I think that's going to be it for new section videos for the year. And I say hold it together because it's about to get a little bit easier, actually. This is about finally now how to do normal distributions about actual data, and it is going to all of a sudden seem a whole lot more relevant, and the calculations make so much sense now that you've had these two sections, 10.4 and 10.5, of prep work just to get you ready for this, all that anticipation I was talking about. Alright, so here's the questions. Notice there's only a couple this time. Number 2 is really like the whole heart of 10.6. It's really what it's all for, and again, that's kind of the crowning achievement of everything up to the last 3 sections. We're able to do this now, and really the calculation is not that bad. Question 1 is a little hard to explain, I guess. Alright, so where's our notes to there? We've spent a lot of time talking about normal distributions and what that curve looks like. Can you follow my mouse? Ooh, on the screen? Normal curve. Okay. That one that we talked about last time was about just the standard normal curve. When they say standard one, they mean the one that is exactly got the inflection points at 1 and -1. It's the the exact one that has this crazy 1 over square root of 2 pi business, e to the negative crazy. Yeah, and that one had that maximum at like 0.39 or something like that. And this one it had an area of 1, which is a big deal. Well, this is all fine and good if you're talking about standard normal distributions where the mean is actually 0 of your data set. But how often is your mean actually 0? This works great for probability when you're talking about what's the probability that the thing is in a certain range here. But in general, you have data sets more like can I turn the page, please? Yeah, there we go. Oops. Like number 2 here, which was the probability the randomly selected American male is a certain height. When you know the mean is not 0, it's something like 70, which is more of a sort of a regular thing to have, and you know the actual standard deviation. Well, here the standard deviation isn't 3, it's 1, and the mean isn't 70, it's 0. So to change this into something we might rather want to see, where the mean is kind of like, now this isn't the axis anymore. I probably shouldn't actually draw it that way. Okay, fine. I'll just erase the whole thing. We want to change that into something where it's kind of lumped over here, and the 0 is way down here. No one's actually 0 inches tall. The mean is actually at 70, and the standard deviation, so these inflection points, are actually at 3 away. If I want to change this graph into this graph, all I have to do, and see here they call this the x-axis and they call this the z-axis. If I want this stuff to stand for this, I let z equal, and here it is. I want to get this backwards if I don't do this right. I think it's really simple. X minus m over s, where here the mean was 70 and the standard deviation of x, they use s now instead of sigma, was 3. Then you just use this, so I would use the graph of this up here. I would be taking the data from the height of the people, and I would just call z my each person minus 70 over 3. And when I graph that, I would get something more like this. And that's what they talk about on page 663. I'm sorry I'm using exactly the same situation they are, but it's a good one to talk about. It's about average height of people, and this mean the standard deviation are really easy to imagine. Now in the book they talk about how to transform this data. Here's how you do it. You make this new graph where that's the representation for z, and you kind of have 2 different graphs of the same data. I think that's really complicated for really what you have to be able to do just in order to answer a question like number 2. I don't want to answer exactly number 2 because that would be a little bit too much of a giveaway for those of you who are participating in the Do Now. Well, everybody participating in the Do Now. I should say those of you who have watched this awesome video. Okay, so what's a similar situation? Let me pause here and type one up. Okay, great question. This is a type of thing where you can use math to determine the truth, sort of. And this is, this is pretty real life. For those of you who've been grumbling about, when am I going to use this in my real life? Well, here you go. Sticking it to the man who's trying to prove to you that his light bulbs are what they say they are. Okay, this one is about light bulb life, which you can imagine, I'm sure. They're saying the testing that they did on the light bulbs, they found out that there is a normal distribution. That's going to happen more often than you probably think. Okay, so there is some sort of... Wow, that looks really symmetrical. I should copy that one. Look at the way the pixelation is just so perfect up here. I'm so proud of myself. Okay. The mean, and of course that's like the median also, because we're talking about standard distribution, everything's symmetrical and happy. The mean here is actually at 1067, and the standard deviation, so the inflection point, if you really cared to label it, would be this distance here is 92. So if you wanted to find out what that is, calculator time. It's 1067 plus 92. I can almost do that in my head faster, but I'd hate to make a mistake. 1159. Just to give you a picture of this, you don't really need to know this every time. I'm just saying one standard deviation kind of looks like... This is what standard deviation means. Standard deviation is kind of the ruler or yardstick we use to kind of describe how the curve is working out. It's 975 there, and it goes on down. And remember about what you remember about the standard curve. When we get to about 3 standard deviations up here or 3 standard deviations back here, there's really not a whole lot of cases that happen beyond that. 99.7% of the area, something's between 3 this way and 3 this way. Anyway, just to give you a picture. Okay, the question is, so somewhere down here, somewhere way down here, there's an 800. And he's trying to figure out what's the percentage of the area that's actually back there. And that's really pretty tiny. But how do you figure this out? Okay, calculator time. Okay, a couple things about this normal Cdf distribution, or function on the calculator. First of all, we want to add up the area from sort of negative infinity up to 800 for this thing. You could sort of convert this to the standard normal distribution by using something like this and then entering it in the normal. Or, remember, I hinted at this last time, the calculator is actually set up where you can just enter things like mean. The things you would need to know would be mean and standard deviation. You can enter these things in where it says normal CDF. You can calculate whatever you need and put in 4 arguments. We were used to doing these 2 last time. This is like lower bound, upper bound. But you can actually put in mean and standard deviation into this thing, and it will already do this conversion. It will already slide the normal distribution curve over to where you want to calculate with it with these actual values. Very handy. Okay, so this one we want lower bound. This is lower. Sorry, looks like an E accidentally. This is upper. This is mean. And this is standard deviation. Can I use mu and sigma? Sometimes in the book they use M and S. Okay, so lower here is really negative infinity. I said before, use like something that's, 5 standard deviations below or something like that. But even to think about 5 standard deviations below in my head, I kind of have to take this 1067 and subtract 5 times negative 92. That's kind of a pain, so I'll show you how I'm going to do that in a second. Upper bound, though, I do want to stop at 800. Okay, and then let's do this. All right, so negative infinity at this point, I found a slick way to do that. You can go, the infinity on the calculator is like 10 to the 99th power, or 10 to the 100th power, something like that. You can do this really fast. There's these little double E capital letters here. That means, you know how the calculator gives you scientific notation sometimes when you don't want it? That's exactly what that's for. You can actually type that little E and do this. So I've basically entered negative infinity here. This is negative 1 times 10 to the 99th power. So if you didn't like 5 or negative 5 or negative 10 being close enough to negative infinity, there you go. And it's really pretty fast to type. So I'm going to start doing that now. It's a little more technically correct. And I'm messing up. Okay, so then we're going up to 800 is the upper bound. Now if I just stop this right here, this isn't going to make any sense. This would be like I'm using the standard normal distribution here. I'm not using the standard normal distribution. I'm using an adjusted distribution that has a mean, check this out, I can just enter this right in, a mean of 1067 and a standard deviation of 92. Give me the area, please, and it is about 0.0018, and that's already a percentage. That's pretty cool. So this is telling me down here it's like 0.0018. I think I should have rounded to 1 more decimal. 5. Fine. This is approximately. So that's like saying 0.185%. That's really tiny. So they're not lying very often. As you're reading this, you're probably thinking, well, you know what, mean of 1067 and a standard deviation of 92, so you just see the word guarantee. If you were the person guaranteeing and you wanted to sell your light bulbs, you might pick a number like, oh, it looks like it's 92 standard deviation, 1,067 hours. 1,000's a nice round number. What if we said, what if the guarantee were instead 100 hours? Can I do this really slick like? I'm going to, give me a second. Yeah, okay, great. Let's change this. Instead, let's say they said 1,000 hours. Then now how much are they lying? 1,000 is like, is like here. And let's see, this is your lying area now. You're lying about this many light bulbs now. It's a whole lot more. Lying about 0.185%, you're probably not going to get taken to court. I mean, if you think about it. Think of all the light bulbs this company probably sells. Only this many people are going to be disappointed. And of those people, how many people are really going to count the hours? Or is it going to happen enough that they think they have a case where they should start counting hours? You'll probably get away with that type of lying. And you know what? In court, that might even stand up. I don't know the laws about that kind of stuff. But if all of a sudden you were going to say, yeah, these things last 1,000 hours, you'd be lying to a lot more people. Let's just see how much you'd be lying. I entered all that stuff already once. I'll just go second entry. I get all that. And I just want to change the 800 to 1,000 now. This is a lot faster on a real calculator. Oh, I changed 3 digits to 4 digits. I have to push insert. Okay. Insert a 1, change that 8 to a 0. Great. Okay. If it was 1,000, now we're talking about 23% of the time, and that is really probably not okay. This is more like 23%, and that 23.32. Yeah, this is a much bigger lie. So that's how you figure that out. Conceptually, there's a lot going on in this problem, but what's really nice about it is the calculator is all set up to take all that stuff. I put that in the notes for 10.5. I sort of hinted that that was coming, and then in 10.6 we go ahead and say, yeah, that's really the case. I think that's it. Let's make sure I didn't skip anything. Yeah, here it is, all in one place, and that's the new stuff. Yeah, great. Oh yeah, okay, binomials. I should talk about this. If you're going to use this same sort of process to estimate a binomial distribution, you got to be a little bit careful, because in binomials, at the start of the way binomials start out life, they're all really these discrete rectangles, like the tossing of heads, and this shape kind of mimics the standard normal curve, or the Chrysler Building, whichever one you like better. But it doesn't get really down to the standard normal curve until this number of n gets really high. Until n is, as we said, if n increases, the number of times you're flipping the coin, for example, this little curve gets smoother and smoother and smoother. The book says n has to be at least 5, which to me seems really low, for this to even be possible. But then the next thing is, if you're going to start chopping this up and say, let's find the area under a curve below a certain point, and we want all the area up to here. Well, you shouldn't really, the problem is about this whole split point. You shouldn't really just use this point as the thing. This is the same problem in the last section. Just sort of a recall how you're going to apply it this time. Say this was exactly, say, 10 heads or something like that. You need to find the area. If you're going this way, if you want to include the 10, these split points here and here are places like, that you'd have to call 9.5, because this is supposed to count one, supposed to be the width of one case. I have to make a width of 1 on all my separators. So yeah, to calculate the probability for 10, I need to start the normal curve, like this curve area between 9.5 and 10.5. It's a little bit of a technicality here, but if I want to count like 10 and below, I'd go from 10.5 down. If I was going to count from, I'd use 10.5 as my upper bound. If I wanted to say 10 or above, I'd use 9.5 as my upper bound. Then it would count 10, and it would count 10 because I need to count a width of 1 for every one of these cases. Again, it only works if n is greater than 5, which I don't think will ever be a problem you have to worry about. But the crazy part is these little things about upper and lower bounds have to be a little bit careful, and that would be the 9.5, 10.5 would be stuff you would have to put in here to grab the right copy of your cases there. Okay, that's it. A little bit sad that I only get to make one more of these after today. Of course, we still have review. We still have review for the finals FST. There's still that. Okay, see you in class.